We made it to Bobby, and here he is right here. And Bobby told us that what we discussed so far doesn't fully complete the picture. The reason why? It has to do with the freedom of particle motion, or the dispersal of kinetic energy. When we look at the previous examples of spontaneous endothermic processes like melting going from solid to liquid, or vaporization going from liquid to gas, or even dissolving soluble salts, or even mixing solid to create spontaneous endothermic processes like freezing onto a wet block, for example, we end up seeing a common feature. And that feature is, after spontaneous change, we see an increase in the freedom of motion of particles in the system. So those particles can be atoms, molecules, or ions, and of course the system for us are chemical reactions. Put another way, we can say that after spontaneous change, the particles have a wider range of motion or kinetic energy, and we say that their energy has become more dispersed or distributed or spread out. So all we want to do now is basically verify this notion of what we saw before, again with those endothermic spontaneous processes. So first, let's talk about the phase change going from a solid to liquid or liquid to a gas. When you have these phase changes, what's going to happen? You are dispersing energy by increasing the freedom of particle motion. We're starting off with more restricted motion in the solid phase, then we go increased particle motion with the liquid phase, and then of course we go to the highest freedom of particle motion, which is going to be the gaseous phase. We can again verify that increase in the freedom of motion when we dissolve soluble salts. So we're again taking a solid and we're going to mix it with a liquid, and that's going to produce ions in solution, along with the solvent molecules, increasing the freedom and dispersing the energy of motion. And of course, when we're thinking of a chemical change, we have our crystalline solids here that again have the ability to spontaneously, through an endothermic process and chemical reactions, the conversion of fewer moles of solids into more moles of gases or solvated ions also result in increased particle motion and therefore freedom and energy dispersion. We can consolidate this and of course this information and say that for a spontaneous process, we're going from less freedom of particle motion to more freedom of particle motion. And again, if you're talking motion, you are talking kinetic energy or the energy of movement. So you can say that you're going from a more localized energy of motion to a more dispersed energy of motion, or a more localized kinetic energy, which I abbreviate as KE here, to a more dispersed level of kinetic energy. Either way, in thermodynamic terms, we understand that a change in the freedom of motion of particles in a system is a key factor affecting the direction of a spontaneous process, okay? So we finally have a small part of the puzzle, motion of particles in a system, that can affect direction of spontaneity. Let's continue to listen to Bobby, folks. Bobby then goes further and tells us to remember what we learned about the quantized energy level of atoms and the quantized kinetic energy levels of molecules, meaning vibrational, rotational, and translational. He says that energy state of a whole system of atoms or molecules is quantized too, folks, which explains why the freedom of motion and dispersal of energy relate to spontaneous change. So let's see how. So just as the electronic energy levels within an atom are quantized, a system of particles also have different allowed energy states. That's the first thing that helps us understand how. Second is that each quantized energy state is called a microstate. And so you can think of a microstate like a snapshot of the system at a specific instant, okay? So that means at any instant, the total energy of the system is dispersed throughout one microstate. The next instant brings a different microstate as energy constantly redistributes among the particles, right? And then third, at a given set of conditions, each microstate has the same total energy as any other, and therefore equally likely. Since each microstate is therefore equally likely, we can apply probability. And Bobby explained that mathematician and physicist Ludwig Boltzmann created a statistical model at the molecular level to describe how many different ways you can arrange the parts of a system, which he called microstates, and represented by the symbol W. So now we can say W equal the number of microstates in a system. You can also say that W is the number of possible microstates that can lead to a particular macrostate. So a macrostate is a way to group microstates. So basically, we take all these microstates that we know are energetically equivalent, and anything that's energetically equivalent, we're going to put into a larger macrostate group. So for this example here, we have one macrostate group with one microstate in it, another macrostate group with 4 different microstates in it, another one with 6 different microstates, another one with 4 different microstates in a different arrangement, obviously, and another one with another one microstate with, again, another different type of arrangement. And so having things in macrostates is going to help us understand and describe the overall behavior of a system without having to look at all the tiny details of each of the microstates themselves. For example, in a system with particles distributed among boxes, as we see here, the total number of microstates is n raised to the power of capital N, where lowercase n is the number of boxes and capital N is the number of particles. So if we were distributing 4 particles among 2 boxes, we'll have 2 raised to the power of 4, which equals 16 different microstates. As we see here, 1 plus 4 plus 6 plus 4 plus 1 is going to give us a total of 16 different microstates. And microstates with equivalent particle arrangements are grouped together and called macrostates. So letter A is a macrostate, okay? Letter B is a macrostate, and here are the different microstates within that. Letter C is another macrostate with 6 different microstates. And again, each of these microstates are going to be equivalent particle arrangements, and not considering the individual particle identities, just their arrangement, okay? And so as you can see, we have 2 particles in both boxes, and so there's 6 different ways to distribute those particles and just having 2 per box. The next thing we can do is layer in that probability. So the probability of a system existing in a particular macrostate, so the probability of us existing in letter A macrostate versus letter C macrostate is going to be determined by taking the number of microstates in that macrostate and dividing it by the total number of microstates. So for example, for the letter A macrostate, there's only one microstate within it. I'm going to take 1 divided by the total number of microstates, which is 16. I'm going to multiply that number by 100, and I get 6.25%, versus the macrostate for letter C, where there are 6 microstates. So that's going to be 6 divided by 16, of course, times 100%, and I'm going to get 37.5%. So as we see, the highest probability or macrostate is going to be letter C because it has the higher number of microstates within it. And so, as we increase the number of microstates, we're going to be able to increase the number of ways to disperse energy. And this concept allows us to understand the probability of different arrangements of particles within a system. We now take this information to continue the hunt for spontaneous change.